as you take a look at this problem, notice it's dealing with a proportion. We looked at some proportions when we were doing our trigonometry stuff, reminded ourselves about that. But basically this is just one element of a general theme for today, which is going to be fractions. Why fractions? Because we're going to be heading into a new unit here on rational expressions and rational equations, which is basically just a big fancy way of saying equations and expressions that involve big ugly fractions. And so we're going to make sure we're good with all the simple fraction work, and then we're going to very quickly accelerate that into some more complicated fraction work. All right, so when doing this one, we got a fraction equal to a fraction, otherwise known as a proportion. When you have a proportion, we are going to cross multiply. And so when we do that, we got 20x equals 198. If 20x equals 198, to solve that then, I'm going to go ahead and divide both sides by 20. Yes, it gives me a decimal. Yes, that's okay. So we end up finding here that x equals 9.9. That's it. That's your final answer. Anytime you see fraction equal to fraction, you're going to use the same technique. It's just that some of them might involve a little bit more complexity than other ones, as you'll be seeing as we go forward. But of course, we aren't just going to be solving proportions. We're also going to have to be combining some fractions by adding, subtracting, multiplying, and dividing them. So let's make sure we remember how to do each of those when we're just looking at some plain old numbers. So go ahead and do each of these operations, please. All right, so let's take a look at that first one. The first one is adding. Whenever we add fractions, what do we have to have? Common denominator. Now, in this particular case, that means I need both the 6 and the 4 to become the same number. Yes, you could just multiply them by each other for that purpose, but there is a smaller one. I'm going to want to use the smallest common denominator I can find, which is going to be 12. And so a great habit when doing these is just start that you're going to have two fractions that are going to be added, and I know I want a 12 to be on the bottom of each. If you get in the habit of building it this way, it helps to avoid some little mistakes that can happen. All right, so to turn the 6 into 12 here, I had to multiply it by 2. So I do the same thing to the 5 on the top. I multiply it by 2, so that gives me 10 12s. In order to turn the 4 into a 12, I multiply it by 3. So I'm going to do the same thing to the 3 on top. 3 times 3 is 9. And so we end up with 19 over 12. Notice the denominator does not change when we add them. If two things have to be the same, it's because they're going to stay the same. That's a nice way to remember that part. Now you could also turn this into a mixed number if you wanted to. That would be 1 and 5/12. But I'm going to go ahead and just leave it like this at the moment. Now, if you did start by just multiplying these two, you would have gotten 24 as your common denominator, and that'd be fine. You could do it that way. Just realize that if you do that, you're going to get down after adding them up, and you'd actually have 38 over 24, and you'd have to reduce that. So always check to make sure that it can't be reduced anymore past that. All right, the next one. It's going to be very similar. Notice it's subtraction, and so I need a common denominator. Well, that's going to end up being the same basic setup then. The only difference is that I'm going to be subtracting on the top instead of adding. And so 10 minus 9 gives me a 1. And we need a common denominator because it stays the same. So 1/12 for that one. All right, next one. We're going to multiply these two fractions. When multiplying fractions, remember we multiply straight across the top and straight across the bottom. And so I could go ahead and go straight to 15 over 24. But you'll notice that reduces. So we're going to go ahead and reduce that. I can divide both 15 and 24 by 3. And so that's going to give me 5 over 8. And we're done. A little side note here. Some of you might have seen I got a 3 on top, and I can divide the bottom by 3. And you might have done that right at the start. You might have turned this into a 1 and this into a 2. And then multiplied. That does work. You're okay doing that. But if you're looking at me like I'm crazy right now and like, wait, how can we do that? Then don't worry about it. Because that's just if you have that technique in your pocket and part of your toolkit, yes, you can go ahead and use that. All right, this last one, we're dividing fractions, which is often the process that we get a little bit rusty on. Dividing fractions is the one where we multiply by the reciprocal. So in other words, I'm going to flip the second fraction, always the second fraction, And when I flip it in the exact same step, not two separate steps, but in the same step, I change the division into multiplication. Now it's just a multiplication problem. So I multiply straight across the top, straight across the bottom. Looks like that reduces, so I'm going to go ahead and need to reduce it. So I end up with the final answer there of 10/9. Now these were all just numbers. Theoretically, this is like 5th grade math or something, right? Theoretically. But of course, we get rusty on these, and so it's good to be able to review them. Plus, it makes for an easy trend when I then start throwing in variables within our fractions. Because the process is now exactly the same. In order to add and subtract, you still need a common denominator. When you multiply, you'll still multiply straight across the top and bottom. When you divide, you'll still multiply by the reciprocal. All those processes are the same. It's just now they're going to be a little bit more complicated to actually execute. And so that's what we're looking at here. These are more what we would call rational expressions, because we now all of a sudden have an x involved. All right, so for that first one, I need a common denominator. It's the 6 and the 4 again, so I already know I'm going to go ahead and use a common denominator here of 12. Because I do like the smallest common denominator, it saves me from reducing later. And so both these are going to become over 12. Notice nothing has changed so far about how I approach it. In order to turn the 6 into 12, I multiply it by 2, right? So I do the same thing to the 5. Gives me 10/12. Still very much the same. In order to turn the 4 into 12, I multiply it by 3. So I'm going to multiply now the x by 3, which is going to give me 3x. All right, I got my common denominator. That means I can go ahead and add them. And when I add them, I know the common denominator is going to be my new denominator. So it's going to be something over 12. That something that's over 12 is whatever I get from adding on the top. So I'm going to do the 10 plus the 3x. Well, notice those aren't like terms. So it's literally going to stay 10 plus 3x. If they were like terms, I would have combined them. But since they're not, we don't. Okay? Next one, the subtraction now. Again, I need to start by having a common denominator. And I'm going to be subtracting the two fractions. So, in this case, 6 and x. To get a common denominator between the two, all I can do really is multiply the 6 by the x. So I'm going to make my new common denominator 6x. If nothing else, when it comes to common denominators, you can always multiply the original denominators together. That will always work. Why don't we always do it that way? Because sometimes we can save ourselves a little reducing by finding something else. But that will always work if you just want to have one method that you got. All right, now, again, we ask ourselves, what am I multiplying by? Like, what do I multiply 6 by to turn into 6x? I got to multiply it by x. So on the top, that's going to become a 5x. And on the bottom, what did I multiply x by to turn it into 6x? By 6. So I multiply the top, the 3, also by 6. So that becomes an 18. I have my common denominators. So now I can go ahead and do the subtraction. Remember, when doing that subtraction, the denominator stays the same. And on the top, I got 5x minus 18. They're not like terms, so I'm just going to go ahead and leave it as 5x minus 18. And you're done. Nothing else can be done there, because you notice there's nothing I can reduce these fractions by. Like looking at 5x, 6x, yes, there's an x in both of those, but there's not an x in the 18. I'd have to be able to pull a number out of all three parts, basically every term on the top and the bottom, in order to reduce one of these. Next up, multiplication. And our multiplication process is still multiply straight across the top, straight across the bottom, no common denominators needed. That actually makes this one pretty easy. I'm going to do 5 times 3 on the top to get a 15. I'm going to do x times 4 on the bottom, 4x, and we're done. A little side note on this one. I cannot turn this into a mixed number. Because of the x being in here, I can't just say like 4 goes into 15 3 times and do like one of these. This does not quite work. So we don't go into that sort of a form. Go ahead and leave them improper whenever you got that variable in there. All right, and last of all, our division. our process for division is still exactly the same. I'm going to multiply by the reciprocal, so I'm going to rewrite the equation as x over 6 times 4/3. Always write out that step. Every now and then I see people who are like, okay, so I know that x will multiply by the 4 and the 6 will multiply by the 3, and they do one of those. And it works about half the time. Because when you do that, you could very easily end up doing the whole thing upside down. And so that's why I always say, write it out like this. Write out what it becomes. And then we can go ahead and do the multiplication. And so in this case, we're going to have 4x over 18. Now you notice that actually reduces, because I'm always looking at the end. Does my fraction reduce? And in this case, I can divide both top and bottom there by 2. So I'm going to do that. So that's going to give me 2x over 9. And now that one's totally done. We talked a little bit in that last section about where we can and can't simplify. We're going to focus on that part here for the moment. So we're just going to simplify each of these. Notice 2 separate problems. I'm not multiplying these or anything. I'm just simplifying the 2 fractions. So in order to simplify, that is, in order to reduce them, I need to find some number that I can divide every term on the top and the bottom all by. And so 24, 12x, and 16 are my 3 numbers here in this first one. What can I divide all 3 of those by? Well, they're all even, so I at least know a 2. Is there anything bigger than 2? Yeah, 4 looks like it would work. Now, if you only saw the 2, you could still do that. If you only divided top and bottom by 2, you'd end up with 12 over 6x minus 8. But then you'd look at that and say, wait, they're still all even. I can still divide them all by 2. And so then you'd have to divide them all by 2 again, which would give me 6 over 3x minus 8. And then it doesn't reduce anymore. But I imagine, and I hope, that you're actually going to be starting and seeing, I can just divide them all by 4 and going straight there. I just want you to see, though, that if you don't find the biggest one right away, it's okay, but it might mean extra steps if you don't find the biggest one right away. Yes, I forgot to divide the 8 by the 2 there. Thank you. Yes, that should be 6 over 3x minus 4. Well done. All right, now for the second problem here. 15x minus 30 over 20. What can I divide everything on the top and bottom by? 5. And so we're going to do that. And so that's going to give me 3x minus 6 all over 4. Can that reduce any more? No, it can't. Because there's nothing else that goes into 3x, 6, and 4, so we're done. Final answer. All right, so for this one, we're adding fractions. Now, certainly these all of a sudden look a lot more complicated, don't they? But in order to add fractions, we need a common denominator. Notice we have a common denominator here, so that's already making our lives a little bit easier. That means that all I have to do is do the addition on the top. And I know that whatever that is, that's going to be over the 2x minus 9. It's going to be over the same thing. When doing that addition on the top, we're combining like terms basically here. So the 13 will combine with the 7. 13 plus 7, of course, is going to be 20. The 4x doesn't combine with anything on its own. And so it all ends up just being 4x plus 20 over 2x minus 9. And does that reduce at all? No. I mean, into 3 of them, the 4x, the 20, and the 2, I can divide those by 2, but I can't divide the 9 by 2. So no, there's nothing else we can do. That's your final answer. So that one looked kind of scary at first, but actually not too bad, right? That's hopefully what you'll find as we go forward on these. So next one, go ahead and multiply those fractions. Right, and so when multiplying these, it is multiplication, so I know that I'm going to go ahead and just multiply straight across the top and straight across the bottom. Now when I multiply on the top, of course 3 times 5, that's nice and straightforward. That's just going to be 15. The bottom, make sure that you really think through what it's doing here. because you could potentially be caught off into a particular error. Because when I'm multiplying x plus 2 by 4, really it's kind of like this. The whole x plus 2 is being multiplied by 4. Or to write it in a way that you're more used to seeing that, 4 times x plus 2. Notice that means we got to distribute the 4 into both the x and the 2. It multiplies by both of them. And so when you do that, you should be getting 15 over 4x plus 8. And then does that reduce? No. Nothing goes into all three of those terms. So we're done. That's it. All right, so if we're dividing fractions, we know the process is to multiply by the reciprocal. So the first thing I want to do is write the first fraction exactly as it was, change the division to multiplication, and then flip the second fraction. All that is one big move, not two separate steps. Remember, every now and then I see people try to make that into two separate steps, and it's just not right. All right, now we can go ahead and do the multiplication. So multiply straight across the top. Of course, that'll be 12. When you multiply across the bottom, remember to distribute the 5 to both the x and the 2 to get 12 over 5x plus 10. All right, now for this one, we're going to be adding fractions. And of course, in order to add fractions, we know we need a common denominator. Well, notice our original denominators here are x plus 2 and 4. Is there any way that I can just like turn this into x plus 4 and this into x plus 4? No, it doesn't quite work that way. Because remember, in order to change these fractions, I'm having to multiply top and bottom by the same thing. There's nothing I can multiply x plus 2 by to turn into just x plus 4. That's oftentimes where people are leaning to go, but it just doesn't work that way. This one's actually more like earlier, where we had denominators of 6 and x. And remember, in that case, I got my common denominator by multiplying the two together. I just made it 6x. This is like that. The only way that I can get a common denominator here is by multiplying them by each other, which means that this first one, I'm going to have to multiply it by 4. And of course, if I multiply the bottom by 4, I'm going to have to multiply the top by 4 as well. And for the second one, I'm going to have to multiply the 4 by the x plus 2, which means I'm also going to have to be multiplying the top by x plus 2. All right, so when you do that multiplication, this is what you should be looking at now. Notice we do have a common denominator, 4x plus 8 in both fractions, which means that now I can go ahead and add them, and I know the whole thing is going to be over 4x plus 8. The only question is, what's left on the top? There, combine the like terms. So you're going to be doing 12 plus 5x plus 10. Notice the like terms here are going to be the 12 and the 10. And so we then get a final answer of 5x plus 22 over 4x plus 8. And yes, that is our final answer because it doesn't reduce at all from there. We could potentially divide the 22, 4, and 8 by 2, but not the 5. That's why it's not reducible. There's nothing we can take out of every single term. All right, so we're next going to be tackling this problem, which oftentimes looks really intimidating at first. But whenever you see something in math that looks really intimidating, there's usually a way that you can manipulate things a little bit to make it more like something that's comfortable. In this case, you got a big old fraction over another fraction. Well, this fraction bar, what operation does a fraction bar really represent? Yeah, it's division. And so this is the exact same thing, just written a different way. All I did is write first fraction divide by second fraction. But this little change in formatting all of a sudden makes it look like something that we've been dealing with fairly recently today, because we now know how to divide the fractions. All right, so once we get it to this point, it's just another division problem. And so we say, anytime I'm dividing fractions, I know what to do. I'm going to multiply by the reciprocal. So I rewrite the problem, And I change the division to multiplication, and I flip the second fraction, always the second fraction. You notice here it's going to make your life a lot easier and a lot less likely to run into errors if you actually write it out that way. Because now I need to distribute. I got to multiply it through, and so the 3 is going to multiply by both 3x and 8. The 12 is going to multiply by both the 4x and the 5. When we do that, this is what we should be looking at. 9x plus 24 over 48x minus 60. It's just that this one, it's not quite done, because it can reduce. What can I divide all 4 terms by? 3. And so since I can divide them all by 3, I do so. And then I check that. Can this reduce any more past that? Nope, doesn't look like it. For instance, nothing goes into both 3x and 8. So those two combined right there tell me, no, it won't reduce anymore. So this is our final answer.